This is the binary game. The bottom right indicates the parts used in this project. There are 8 switches as you can see, with each switch representing a different bit. To demonstrate, I will turn on each switch as its output will be presented on this bar graph. And for each flicked switch, I'll provide its corresponding binary, hexadecimal, octal, and decimal value on the bottom right from the serial monitor from the Arduino Nano. So this is the first bit. That's the least significant bit. The second bit. Third one. Fourth. Fifth. Sixth. Seventh. And the final one, which is the most significant bit. Here is the value of each bit in binary. So the first switch would represent 2 to the 0. The second switch would represent 2 to the first. And this would continue on till the last switch, which is the 8th switch, is 2 to the 7th. And we can interpret this binary value into decimal, which would be in powers of 2. So you go 1, 2, 4, 8, 16. And this, as you can see, just multiplies by 2, follows an exponential pattern. And the sum of all these bits can be expressed by the equation 2 to the n minus 1, where n is the number of bits. So in this case, we have 8 bits. So we would put in our formula 2 to the 8 minus 1, which would give us a value of 255, giving us the maximum sum these 8 bits can produce. This graphic depicts how the Arduino Nano manages to produce its output, which is dependent on 3 pins: data, clock, and latch. For the shift register's output to change, the clock must be on its rising/positive edge, and data must be high. As shown, the shift register alternates from 1s and 0s to 0s and 1s. However, the shift register output is not presented on the storage register until the latch pin is on its rising edge. Every time the latch pin goes high, the output present on the shift register is latched and thus transferred onto the storage register. This register now alternates between 1s and 0s and 0s and 1s. Here is the shift register chip, the HC595, used in the project, where outputs Q to A to Q to H represent the bits connected to the bar graph. Pin 8 is ground, while pin 16 is VCC. Pin 14 is the serial input pin, otherwise known as the data pin. Pin 13 is the output enable pin. When it's high, the output pins are disabled. Pin 12 is the register clock, also known as the latch pin. Pin 11 is the shift register clock, which is activated on the clock's rising edge. Pin 10 clears the shift register, setting the outputs all to 0. Output 9 outputs the same bit as Q to H, which is useful for connecting multiple shift registers. Here is the code for the project. In the setup, pins 2 to 9, the state of each switch on the switch bank, are set as the input, as well as data, latch, and clock, using the pin mode function. In the void loop, the variable assemble, which represents the binary state of the switch bank on the serial monitor, is 0. Then, bits are shifted using the bitwise OR operator as each input is being read, either low or high. Here is the table demonstrating the OR bitwise operator with the values shown in binary and decimal. Once that binary value has been shifted to the left, latch is set low. Then it is shifted to the serial monitor. Latch is set high so that the outputs can be transferred from the shift register to the storage register. Finally, the value of the switch bank is printed in binary, hexadecimal, octal, and decimal. The last line is meant to produce the output only when the inputs change. Here are the values presented from the switch bank onto the Moreland bar graph.